Dear students, welcome to Commissionerate of Collegiate Education Learning Management System. In this video presentation, I am going to discuss about critical solution temperature. Myself, Vinny Teja, lecturer in chemistry, SKR and SKR Government Degree College for Women, Kadapa. In this video lesson, I am going to focus on critical solution temperature and different types of critical solution temperature like systems with upper critical solution temperature and the systems with lower critical solution temperature and the systems with both upper as well as lower critical solution temperatures, and finally on the effect of impurities on critical solution temperature. Some liquid pairs do not give homogeneous solutions at all compositions. Such liquid pairs are said to be partially miscible liquids. Some examples of such liquid pairs are phenol water system, ether water, and aniline water, etc. Two solutions of partially miscible liquids which are in equilibrium are called conjugated solutions at a particular temperature. The two layers of a conjugated solutions become completely miscible at a certain temperature, whose value depends on the nature of those two liquids. The temperature at which two partially miscible liquids become completely miscible at all proportions, that temperature is called critical solution temperature or consolute temperature of the system. When the critical solution temperature is lower than the room temperature, it is called lower critical solution temperature. When the critical solution temperature is higher than room temperature, it is known as upper critical solution temperature. Depending on the critical solution temperature, partially miscible systems are categorized into three classes. They are partially miscible systems with upper critical solution temperature, for example, phenol water system. And the second type is partially miscible systems with lower critical solution temperature, with example, triethylamine water system. And the third type is partially miscible systems with upper as well as lower CST, with an example, nicotine water system. Let us discuss each type of CST in detail. Coming to the systems with upper critical solution temperature, the example is phenol water system. When roughly equal amounts of phenol and water are mixed, two layers are produced, viz. A solution of phenol in water and a solution of water in phenol. The composition of each of these layers is fixed at any given temperature and can be determined by the analytical methods. At temperature T1, small amounts of phenol added to water, it dissolves completely. If you observe the graph, the points A, B, C represents the composition of liquid mixture after addition of different amounts of phenol to water. If the addition of phenol is continued, solubility limit L1 is reached. If more phenol is added, it will not dissolve in water and a second liquid layer is formed. Similarly, the points D, E, F represents the composition of liquid mixture after addition of different amounts of water to phenol. If the addition of water is continued, the solubility limit L2 is reached. And if more water is added further, the water will not dissolve in the phenol and a second layer is formed. Therefore, region to the right of L1 is a two-phase region. Similarly, region to the left of L2 is a two-phase region. Therefore, between L1 and L2, there exists two liquid layers, that is called conjugate solution. Hence, it is a two-phase region. This whole region is a two-phase region. If we increase the temperature, the solubility of water in phenol and as well as phenol in water increases. At higher temperature, that is above T1, solubility limit will increase from L1 to L1 dash, similarly L2 to L2 dash. By joining the points L1 and L2, a dome-shaped area is formed. If the system is warmed further, the amount of phenol in water layer as well as the amount of water in phenol layer increases. At a certain temperature, the two layers become one layer, that is, the solution becomes homogeneous. This temperature is called critical solution temperature for phenol water system, and it is found to be 66 degrees centigrade. And the composition at 66 degrees centigrade is found to be 34% of phenol by weight. If you observe the graph of phenol water system that shows upper CST, above this critical solution temperature, the two liquids become miscible with each other in all proportions and the solution exists in one layer. When mutual solubility of water and phenol is plotted against temperature, a parabolic curve is observed. And this graph leads to the following significant conclusions. Whatever may be the composition of phenol and water, at and above 66 degrees centigrade, both are completely miscible with each other. At any temperature below 66 degrees centigrade, within the range of this parabolic curve WOP, there are two layers in equilibrium. The composition of one layer corresponds to the point A and that of the other point B. And the line AB is called tie line. At any temperature below 66 degrees centigrade, if the composition lies outside the curve, we get only one solution. For example, if the composition lies on the left of the curve WO as represented by the point X, the mixture will then consist only of unsaturated solution of phenol in water. That is, the percentage of phenol is less when compared to water. On the other hand, if the composition lies on the right of the curve O and P, as represented by the point Y, the mixture will then consist only of unsaturated solution of water in phenol. That means the water quantity is less when compared to the phenol. Hence, in this type of system, the mutual solubility increases with rise in temperature. Some other liquid pairs with an upper critical solution temperature along with corresponding composition are given in this table. Aniline and water shows critical solution temperature at 168 degrees centigrade with the composition of 40% of aniline. Coming to the aniline and hexane, the critical solution temperature is 60 degrees centigrade with 52% of aniline by weight. Methanol and CS2 have an upper CST of 49.1 degrees centigrade with 29% of methanol by percentage weight. Similarly, methanol and cyclohexanone system shows the upper CST of 40.5 degrees centigrade with 20% of methanol by weight. The second type of system is the systems with lower critical solution temperature. The example for this type of system is triethylamine and water system. In this system, the mutual solubility of two liquids increases with decreasing temperature. Thus, cooling of this system to 18.5 degrees centigrade temperature causes the two components to become completely miscible with each other. This temperature is called lower critical solution temperature or lower consolidate temperature of triethylamine water system. The systems that follow lower CST shows the similar graphs like this. And this graph leads to the following important conclusions. At and below 18.5 degrees centigrade, the two liquids are completely miscible in all proportions. And the system is said to be homogeneous and exists in one layer. Above 18.5 degrees centigrade, two cases are possible. When composition of system lies within this curve, the two liquids are not completely miscible and the system is heterogeneous and thus two layers exist. When composition of the system lies outside of the curve, only one single layer exists. Other examples of lower critical solution temperature are diethylamine water system with 43 degrees centigrade and 13% diethylamine by weight. And the second example is 1-methyl piperidine water system having lower CST of 48 degrees centigrade having 5% of methyl piperidine by weight. The next type of the system is the systems with both upper and lower critical solution temperatures. The example for this type of system is nicotine and water system. In this type of system, the mutual solubility of two liquids increases with both increase of temperature as well as with decrease of temperature. In other words, these liquids are completely miscible at certain high temperature as well as at certain lower temperature. Between these two limiting temperatures, they are partially miscible. The systems that follow this type of CST shows similar graphs as shown here. Nicotine water system has two critical solution temperatures. They are 208 degrees Celsius, at which the system contains 32% of nicotine, and 61 degrees centigrade CST, at which mixture contains 22% of nicotine. Within the closed area, at any point, there are two layers. Outside the curve, there is only one layer. The systems with upper and lower CST are affected by pressure. With increase of pressure, the lower critical solution temperature is raised, whereas upper critical solution temperature is lower gradually until they become 1. In other words, as the pressure increases, the closed area becomes smaller and smaller until they become a point. Therefore, at higher pressures, the liquids are completely miscible at all temperatures and in all compositions. Till now, we have discussed about the types of critical solution temperature. Now, let us understand how the impurities in the liquid pairs affects the CST. The addition of an impurity which is soluble in partially miscible systems increases the miscibility. This process is known as blending or salting out in pharmaceuticals, and it is used to select the best solvent for the drugs. In this process, a salt or an impurity is added to separate the aqueous phase from the organic phase. If the added salt, that is an impurity, if it dissolves in one of the liquids only, then it results in an increase in the upper CST and a decrease in lower CST. Further, if the added salt is soluble in both the phases, then the upper CST is lowered, whereas the lower CST is raised, thus increasing the miscibility of the system. This increase or decrease in the CST depends on the nature and the amount of the added substance and the composition of the system. Let us summarize the points that we have discussed so far. Liquid pairs that do not give homogeneous solution at all proportions are called partially miscible liquids. The temperature at which two partially miscible liquids becomes completely miscible, that temperature is said to be critical solution temperature. Depending on the critical solution temperature, the partially miscible systems are categorized into three types. They are systems with upper critical solution temperature, and the systems with lower critical solution temperature, and the systems with both upper as well as lower critical solution temperatures. We discussed that in the systems with upper critical solution temperature, the mutual solubility increases with increase in temperature, whereas in the systems with lower critical solution temperature, the mutual solubility increases with decrease in temperature. Whereas in the systems with both upper and lower critical solution temperature, the mutual solubility increases at certain higher temperatures as well as at certain lower temperatures. That means between these two temperatures, there is partial miscibility. That means it exists in two layers. And lastly, we discussed about the impurities effect on critical solution temperature. The addition of impurity which is soluble in partially miscible systems increases its miscibility. I hope you have understood this presentation on the topic critical solution temperature. Thank you.